Hello everyone. So quick question. How many of you have used ChatGPT? Show of hands. Okay. Now keep your hands raised if you were amazed by the things that you saw the first time you used it. So look around you. You can see that almost the entire room has their hands raised. Have you, in the last decade, seen any piece of technology that has such adoption? I know a lot of people at work, right? They don't, our previous speaker mentioned, they don't use Instagram, they don't use Facebook, but ChatGPT is definitely within their bookmarks, right? And today what we are looking at is going to be how we can build open source generative AI agents that enable us to offload some of our tasks to them. So it's going to be something that we build upon from the previous talks, right? And I call this into the LLM-Verse because it's really a rabbit hole. I've started on this journey about a year back and I'm like, I am well deep, right? So generative AI. If I go into the weeds, right? It's been 8 months approximately since I've gone a single day without hearing the word AI. Right? Everywhere you go, there is AI. As a software engineer, it's in my Jira. It's where I do my Scrum. It's also where I do my code. It's there in my IDE. But this is not just an engineering thing, right? The medical community is using this. So is media. People are doing creative things with it. So are the folks who are managing people. So it's just everywhere, right? And it's really difficult to avoid it. So we embrace it. Before we jump into the actual topic, I'll tell you a little more about myself. My name is Amith. I currently work with Unisys as a senior engineer under the AI enablement group. What we do here is we take artificial intelligence and we infuse it within our company's processes as well as our clients' outcomes so that they're all happy, right? And a little bit more, I've been contributing to open source software since I was 12. I'm an advisor here at OSI and I'm the lead maintainer for the Digital Bill of Materials project, which is around software supply chain security and led by the Linux Foundation. I love teaching and hosting workshops, and when I'm not doing all this, I'm tinkering with electronics at home. So that's where we're at. A little bit of a disclaimer, all the opinions that I express here are my own and does not reflect that of my employer, which is Unisys. So I know it's almost 1, right? All of you are hungry. Unfortunately, I can't provide you food at the moment. However, I can provide you knowledge, and this is what's on the menu today. We will look at what an LLM is. How does ChatGPT work, right? So interesting. We'll look at how you can effectively use ChatGPT and other large language models. We'll see how you can use open source tools that does your work for you. And finally, we'll look at all the tools that made that possible, right? So when you look at it, what is an LLM? What makes it special? You've all texted, right? Is there anyone in this room who has never sent a text or a WhatsApp message? 0 hands, right? And every time you text, you would see your keyboard trying to predict the next word. It doesn't do a great job all the time. And sometimes you'll note that it does a very terrible job. But over time, it learns, right? And that is autocomplete. Let's give autocomplete steroids, and that's where you get large language models. So at its core, it's just autocomplete. Now, you might be thinking, yeah, that can't be true, right? So let's dive into how that works. If you're looking at it from a technical perspective, large language models come under deep learning. So in fact, almost all the large language models today are neural net based, and that is of course part of deep learning. And additionally, it's this architecture called transformers. Since this is not an ML class, we'll not look into transformers, but we'll see how it works at a high level. Now let's take a trained large language model, and this was the pre-trained models that Asta was talking about earlier during the AWS session, right? This is already trained against a large data set, has a lot of parameters. Now I told you, the task is autocomplete. That's what we're trying to achieve. So let's say I'm putting in some input, right? I am presenting. This is what is known as a prompt. Any input to a large language model is known as a prompt. You'll note that it's not exactly how I'd enter it, right? It's I am presenting. Why is that split, right? The reason is that large language models don't see words, they see tokens. That's the language that they speak, right? A token can be one word, multiple words, or part of a word. That's all dependent on how the model was built. And there is this tool called a tokenizer. It runs before the model is fed with data, and the tokenizer determines how the data is split. So there is a rule that you have to use the same tokenizer that you used while training in order to do inference. Finally, this is an important limitation that I want you to keep in mind. A large language model at any time can only deal with a limited set of tokens, which means that your input is limited. Now, I lied a little bit about the words. What the large language models actually sees is these numbers known as vectors. So the token I will always be 23. The token am will always be 234. So that's a property of the tokenizer. Now, let's move some of this away. And let's go back to the key task at hand, right? It has to find the next number in the sequence, which is, it sounds like a simple problem. But what it uses is this architecture called a transformer, which is powered by this mathematical mechanism called attention. Now, we don't have to get into attention to understand this. Just understand that it is a black box that generates a list of probabilities based on I am presenting what is the next most relevant word. You'll see a set of candidates that it's picked. At is the most likely candidate. We have on, today, etc. secondary candidates. Just remember, keep this in mind for later. There's also usually a stop token. So this is a special token that the LLM emits to say that I'm done generating. There is no more output. You can stop, right? And finally, that generation occurs. So wait, you're like, okay, you've used ChatGPT and it's chat, right? Like it's not a keyboard, it's not autocomplete. How does chat work? Now, if you really generalize the problem, chat is just a special case of completion. If you put in a completion prompt that's like user, hi there, assistant, hello, how are you? User says something, assistant, please complete, right? So that's how chat works. Chat is essentially a special case of completion. Jumping into it, what makes large language models large? Two key things. The first thing is large data set, right? We ingest billions of websites, billions of pieces of content over millions of topics. So it's pretty much seen everything that a human has written and published in the last century or so. And the second thing is large parameters. So in deep learning, without getting too into the weeds, think of a parameter as a unit of thinking that the neural net has. The more the parameters, the bigger the brain, right? And what this did, and researchers did not know that this would happen when they did it, is that it brought about emergent ability. So in science, what we call an emergent ability is something that does not appear at small scale, but as you scale things up, right, it starts to appear. In this case, the emergent ability is to talk like a human, to generate the next word like a human. And we never thought the original researchers, for example, the folks who did attention is all you need, the original paper that started all this, did not envision this, but it was something that was observed. Additionally, the resultant models are general purpose. A lot of you, how many of you have used ML models in production in any of your work cases? Yeah, some of you, right? And you would have noticed that you have very domain-specific models, right? You have one for a specific fine-tuned use case. That's not how you work with LLMs. LLMs are generally general purpose due to the vast training that they've gone, and they can do a wide range of tasks pretty well. Diving into it, this is a warning. Now, you've seen what ChatGPT can do, but at the end of the day, it is a probability machine. It's just predicting the next most likely word. It also sounds very human because it's learned from human text, right? This means that it can easily make things up because it doesn't really reason. It's just predicting the next word. And this is very believable, and this is a problem. And we call this hallucination. We'll look at how to deal with that later. So basically, don't trust anything that comes out of this model verbatim. Don't put it in your critical processes without a human verifying the outputs, right? So this is also a new frontier for using AI. I've looked at the industry and I've seen that there are so many people getting into AI right now. If you look at the list of people graduating with an ML degree and the list of people doing AI /ML, there's going to be a disparate difference, right? Because there's a lot more people going into AI. And that's because of a key thing, right? At this point, we've shifted to using the pre-trained models for like 90% of the use cases. Before, if you wanted to do an ML thing, you build an ML team. You have a data scientist, a data engineer. I don't need to put out a job board here. You know what ML entails, right? We don't need specific data sets. You would have listened the keynote as well as the prior talks that data sets is the hardest part. Well, don't need them because the pre-trained models work great for a lot of use cases. Now you have to think in terms of prompt design and parameter tuning. Parameter tuning is fairly obvious, right? Like, turn the knobs. But what does prompt design mean, right? That's a new word. So let me use that to segue to the next piece. How do you use LLMs effectively? I say that it is an art and a science because there are high-level guidelines that help you progress. However, for a specific use case, you need to try them out and see what works. There is no one size fits all formula. Let's jump into it, right? There are 3 levels, and these levels are in terms of ascending difficulty and in some cases ascending cost, right? The first one is prompt engineering. Second one is adjusting parameters, and final one is fine tuning, which the prior speakers have touched on a little bit on. So if you look at prompt engineering, this is the textbook definition, right? If anyone's going to go write an exam on generative AI, they can capture this. But essentially, what this is you take a specific instruction given to an LLM and you optimize it, get you better results, 1, and 2, reduce your token usage because that's what you're paying for. So how can you get the best result with the least words told to the LLM? That is the art of prompt engineering. Let me show you an example of how a small difference in the prompt can cause a big difference in your output. And I'm going to pull out ChatGPT for this, and I'm going to use this technique called few-shot prompting. Few-shot prompting is where you tell the LLM, I want this done. Here is an example. Now do 10 more like that, right? So I'll give you an example here. I'm trying to generate synthetic data. I'm a machine learning engineer. I need to do a little project. I need to create synthetic data. Large language models are great at doing this. So first I've asked, create a fictional user list with name, address, phone number, gender. It's given me a list, but it's not in the form of a table. I actually did not want the USA at the end. I wanted the prefix for the phone number. I could sit down and write these rules one by one, and they would take so much space, right? Instead, what I would do is I'll give it an example. I've given it in the form of the table. I've given it the header. I've given it one sample row. Now, based on this row, the exact same large language model without any parameter change or without any fine tuning has given me a totally different result, one that I can directly use in my development, right? So this is the difference. So adding that one example has entirely changed the way the LLM has given you an output. And this is the power of prompt engineering. So always provide examples and ask the LLM to adhere to your preferred format. And this is just one, and of course there are websites that provide you hundreds of different specific things that you have to take care of. So let's see adjusting parameters. Now in ChatGPT you cannot adjust parameters, but if you are running an open source model or using something from the cloud, you're able to adjust these parameters. We'll touch on one important parameter that is almost used in every single use case, which is temperature. I've had someone actually ask me if this means that they're going to turn up the heat of the server running the LLM. It's not. So this is in sense of physics, right? Increasing temperature equals increasing entropy, the randomness in the system. So remember, I told you to keep that in your mind, right? That list of possible tokens that is generating. You saw this probabilities next to it, 0.96, 0.94, so on and so forth, right? Temperature sort of mixes those up. Lets less likely tokens leak out of the large language model. Let me explain this to you with an example. I'm going to give a prompt to a large language model saying, complete the following statement. The sky is, and I'm going to run the same prompt with different temperature values, right? At 0 temperature, which is the least temperature that you can get, you can see obvious completions. The sky is the limit. The sky is blue. The sky is overcast. Stuff that you'd see in books, stuff that you see in the training data set. Let's increase it, 0.5 temperature or 5 temperature. Now you get longer responses. It starts getting more creative, right? The sky is not the limit. The sky is almost perfectly blue. The sky is gray and airy. And this is still reasonable results. What happens if I just take the knob and I break it? I just put it all the way to 10. What happens is the sky is clear, water is smooth, there is randomly a dolphin, and now a kingdom is also involved. This is a perfect example of hallucination, right? But sometimes hallucination is good. If we are doing something technical, the thumb rule is this: doing something technical and precise, set temperature as close to 0 as possible. Are you writing poetry? Are you writing stories? Set it close to 10. Right, so there is no perfect. You can't tell me that I have this use case. What temperature value should I use? I can't give you an answer because there is no canned response there. You have to try it out and get those answers. Now let's say you did prompt engineering, you did temperature tuning, you did all the other parameter tuning. Still, the results aren't meeting your expectations. That's when we bring out the big guns. And the big guns is fine tuning. I call them big guns because this is prohibitively expensive compared to the other thing. So from an organization's perspective, probably a drop in the bucket. But for an individual, it's definitely incredibly expensive. This involves taking the pre-trained model, the foundation model, and we are going to take a little bit of our data set and do the final few training cycles only. This is not recreating a model from scratch. Right? That would take way too much resources. But the caution here is that only use this as a last case resort. Don't jump to fine tuning the first time you see it, right? Because there are various disadvantages here. The first one being that if you're using a cloud API and if you fine tune something and you deploy it, right, the cost for tuning is there, so that there's a training cost. Additionally, every inference you make with that model, every token you predict with that model will be almost 5 to 9 times more expensive if you're looking at OpenAI's service. Right, so if you can solve it with prompt engineering with like 1/4 the cost, why would you do fine tuning? It can also reduce performance on general tasks. So as a human, if you've gone to a specialist doctor, like some specialist doctors at least, right, you'll note that they see every problem, like it's like they have a hammer and they see every problem as a nail. You go to the kidney specialist and everything is a kidney problem suddenly. That happens with large language models as well. If you make a model very good at, let's say, medical tasks, it starts getting worse at general tasks. So if you want a generalist model, don't fine tune it. Finally, this is a carve out, right? Every rule has an exception. If you're using an open source model with a few parameters, it makes a lot of sense to fine tune because to begin with, you did not have that generalist capability. So you're not going to lose anything. You're actually going to make it better at a specific use case. And in our experimentation, we found this to be very useful. Now, challenges. We've talked about the challenges a little bit, right? Now, let's collate all of them. I mentioned that you cannot trust the models, right? There is no traceability source of information. ChatGPT doesn't tell you where it got its info from. If you ask it, it's going to make something up. Right? It's going to say, I got it from this journal. You try revisiting the journal doesn't exist, neither does the website or the author. Right? So it's like an absolute question mark. Now, I'll tell you, okay, go validate your sources. But as I mentioned, ChatGPT does not give you the sources. So where do you go to validate, right? Finally, prompt sizes are limited. What if you want to search against like a big book, right? And what if you want to retrieve the news? The news changes every day. You cannot fine tune your model every day unless you're like Ambani or something, right? Like you can't sit and keep spending thousands of dollars every day just to get the latest news. Now, how do we tackle this? Now, squint a little bit, look at these slides. Now, think to yourself. Some of these problems are very familiar. Don't think AI/ML, think in your own life. Think, go back to when you were a student, or some of you may be teachers, right? Go back to when you're teaching students. A lot of these problems are actually human problems. Let's reframe them, right? Humans are notorious for making things up without references. Misinformation is everywhere, right? And half the time, if you ask a student to complete an assignment, they're going to copy from Google. Now it's ChatGPT, but before Google, right? And they're not going to tell you where they got it from. How would you validate? And finally, I don't know about you. I'm horrible at memorizing stuff. If I try memorizing stuff, it's as good as asking me to do a backflip. I can't do either, right? So, and memorizing is difficult, slow, and human memory itself is limited. So how do we solve these problems? Does anyone want to just say one word? How do we solve these problems? We templatize it. Someone said Google. That's a great answer. We give ourselves tools, right? We give ourselves Google search. We give ourselves books. I attended a meeting yesterday. I write meeting notes and I refer back to it. Right? That's how I keep my memory fresh. It's not that I keep it all in here, right? We are going to solve the same problem for LLMs with the same tool. So essentially the same problem space. Let me introduce to you retrieval augmented generation, or commonly abbreviated as RAG. Right? We have been talking to the large language model, the big boss in the background that's generating the text. Now what we're going to do is we're going to add a middleman, the LLM orchestrator. The job of the orchestrator is to combine together this large language model and the vector database. So we are generating text. What we are going to do is we are going to augment that generation with some retrieval with this vector database. Now, vector database I know is a new term. In the interest of time, I will not get into it. Right now, you can treat it as a black box where you can perform a search. It returns a subset of your content, whatever you ingest into it, and it almost always gets you the right answers. Just assume that it's a black box for now, right? And essentially, whenever a user asks a question, every single answer will come from the database, will be referenced from the database. Let's see this in action, right? RAG in action. Now, let's say the user asked the question, who founded the free software foundation, right? It's a very normal question. You ask it ChatGPT, you'll immediately get the right answer. But I want references. I want to know where it came from so that I can validate it. So this is a simple example, but this generalizes to a lot of use cases. So I'm going to go and after this user question, what we get is the orchestrator is not going to ask the LLM that. It's going to prepare a brand new prompt which says, who found the FSF? Don't give me the answer. Give me a search query. Give me a search query that I can run against my database. Do not give me the answer. So what the LLM returns is no longer the answer to who founded the FSF, but the two words, FSF founder. These are the things that I want to search for against in the database. So now the orchestrator stops the LLM, like, thank you for the answer, and it actually goes and runs that query against the database. Now we have the results, right? Like we have 3-4 results on who the founder FSF, right? Now the orchestrator calls the LLM another time. This time it's like, hey, you asked me to search for FSF founder. Here are the results. Here was the user's original question, who founded the FSF. Now give me the answer and give me citations as well. Now the LLM within its prompt context has everything it needs to answer the question. The LLM returns and answers, and what you get is the FSF was founded by Richard Stallman, and you get a reference. Now I can go to Wikipedia FSF line 25 and verify that Richard Stallman indeed founded the FSF without me worrying about hallucination, right? So this solves a large class of the problems in the sense that now you can use large knowledge bases. I can ingest books that are hundreds and thousands of pages long. In your work life, you might have support knowledge bases, right? You might have knowledge bases in your product, right? Now you can ingest the entire knowledge base of the product at any given time, and you can use it reasonably with an LLM, even if it has a limited context size. Now data can be updated. Now news, right? You're retrieving news. If you ask the LLM, what's today's news? Can you give me a summary? Now it can actually retrieve the news because it's as simple as a database update. No fine tuning required. It takes milliseconds, right? So live data, like let's say if you have customer data flowing in, if you have, if it could even be stuff like, you know, are the lights at home turned on, right? Like live data can come in and the LLM can answer questions against that. And finally, it's easy to verify data. We have citations, right? Like, so we can actually click through and indeed see that, okay, this is the correct piece of data. Now, no, there is no, I'm sorry to say that nothing will actually solve hallucination. This is a workaround. The workaround doesn't work all the time. LLMs can still hallucinate. We've had several production situations where, you know, you have the prompt, you have the citations, but the LLM cites the wrong one that was returned. Or the LLM decides that I don't need citations today and doesn't cite. So inherently LLMs are stochastic. They are probability machines, and this is, you never get the same answer twice, right? So this is to be expected, but this vastly works around the problem. Global context is absent. So remember, we are taking parts of the data and we are answering the question. We're not, let's say 10,000 page book, right? You're not giving the full 10,000 page book at a time to the LLM. The LLM can only see those parts that were retrieved. That means that global context queries will not work, which is to say that if I ask something like, how many times did Alice say hello in this book, right? To answer that question, you have to read the whole book, and we are not retrieving the whole book. Therefore, these classes of questions are prohibitive. They cannot work. Finally, latency. Now, what was usually just one call to the LLM has become one call to the LLM, a call to the database, call back to the LLM, return back to the user. Multiple round trips increase latency and therefore degrade user experience. There are ways to manage this, which I'll not get into. Now I'm a little bit of a thought experiment. Let's take this one step further. Instead of asking for a search query, we are asking for a search query, it's returning it, right? Let's ask it for an API to call. Let's ask it for the arguments to that API. Let's say there are smart bulbs here. Instead of doing retrieval, say that turn off lights is a function, and you're able to pass a light number. You ask the LLM to actually generate the function call for you, not a search query, right? And second thing is, right now we force the LLM to do. The orchestrator essentially takes the query, asks the LLM, does the retrieval, and goes back to the LLM. That is a static flow, right? Like the orchestrator always reaches out to the database. The LLM gets no say in it. What if we take that paradigm and shift it? Don't control from the orchestrator, give the LLM the control. Tell the LLM, you tell me what to do, I will execute it and give you the answers. And enter agents. General purpose, large language model applications that can interact with the world around it, that can interact with websites, that can interact with apps, that can interact with hardware, right? And to just sell this to you, I'm going to go demo first, because even I only believe things when they're actually demoed. So, okay, so before I play the demo, right, on the left is my agent, right, and on the right is a browser. This is your bog standard Chromium browser. The special thing about this browser is being controlled by this LLM. So the LLM can now issue commands for the browser to go anywhere, or click any link, or see what's in the browser. So the LLM has a view into the browser. So I'm going to give it a simple query. Go out, I don't care, to the internet or wherever, find out everything you know about Amith KK, the software engineer, and use a few sources. So what I'm going to do is I'm going to hit play here, and you'll see me typing the query into this thing. So it's like, give me a brief summary of Amith KK, the software engineer. So in case there are other Amith KKs in case, and I'm asking it to use at least 3 sources. Now, as soon as I do that, you can see what happens. It's thinking, right? And it's thinking, and the first thought it got was, hey, let me Google stuff. And it's actually gone and opened up Google on the browser, and it's actually trying to extract text from it. So right now it's already started executing commands like a human. So that's what's happening here. We'll dive into how this thinking process works a little bit after the demo. And I'm going to now continue. I've paused it automatically here. So the next thing is, it's actually looking through the links and seeing which links make sense, right? And at this point, it's getting a thought that, okay, maybe I should check LinkedIn. Now we've gone to LinkedIn. Now this browser is not logged in. This browser does not have my Google account. This browser has no browser history. So LinkedIn is suspicious. This is probably a bot. So it's given me the bot page. Oh no, right? Your traditional scrapers will be like, oh no, this is the point at which we have an issue, right? But now you'll see something that is very interesting that the LLM does. The LLM has detected that it has failed to do this task. It said that, oh, I can't access it, and that's probably because there is some sort of bot blocking. Now the LLM has to come up with an alternate approach to solve the problem. So instead, now if I hit play, you'll see that the next action it does is it stops going down the LinkedIn path, and it actually opens the office hours page, which actually mirrors LinkedIn, right? So, and it's actually pulling data from an alternate source. So it's reasoned, and it's found out that, okay, let's go here and get the data instead. Now the next piece is it's also gone to my old website. It's pulling data again. This is all driven by that initial Google search query that it did, right? And finally, after getting all those inferences, it's finally creating an answer. It's at the point at which, okay, I have everything I need to make the answer. It's referred to how many ever sources I've asked it to, and here is the answer. Now, a few things to note. This looks fairly magical, but what I can say here is that it did not totally follow my instructions. I said use at least 3 sources. It didn't use 3 sources. It failed at LinkedIn, used office hours and my website, right? So technically it didn't use 3 sources, so it doesn't follow your instructions exactly. But this is far more advanced than just doing retrieval augmented generation. Now let me show you how this is like a simple use case, right? But you can imagine the same thing being extended to apps. That's what Windows Copilot is. You can imagine the same thing extended to your applications, where you can call various functions and workflows that the LLM drives. Right? And if you can add a human approval step as well, like before you go to this website, do you want to approve? So you have those capabilities. So let me show you how this generalizes. I'm going to ask you a totally different query that's not related to people, and this is actually my research bot. Right? I use this at work to actually quickly find things out and summarize them for me rather than me browsing. Right? So this is one of the ways where you can offload some of your tasks to the large language model. So going to the next little demo. This time I'm going to ask of it a different thing, right? I want to find who are the top open source contributors on some generative AI repository. I don't care which one, let it pick, right? So I just want to find that out. Remember that this large language model has never been trained to do this task. It's just generalist capabilities. So I'm going to hit play. So I'm going to give it the prompt, get me the list of top contributors. First thing is, okay, let me go to GitHub, right? So it opens up GitHub, right? And as it opens up GitHub, now it doesn't know where to go. So now it's querying various parts of the page. Remember, the LLM can't take in the whole page at once because of limited context, but it's working within that limitation and looking through the parts of the page. Finally, it's found a way to actually click through a link, and it's going to navigate to Generative models, one of the top repositories on GitHub. And now I've asked it to find contributors. Now it has to figure out, okay, how do I get to the contributors page? It's doing that. So it's trying to figure out, okay, what's the text? What are the pieces? It's finally reached the contributions page. Another roadblock, it's loading, right? Now it's trying to extract the text, loading fails, but it's still loading, right? It actually reasons with that, figures out it's loading, let me try again after a few seconds. And it did that. And finally, after that, it's automatically created a CSS query to get just the names of the people from the page. And it's building a final answer, and these are my top contributors to this repository, and it's chosen the repository for me. I did not have to do any thinking. The LLM did the thinking for me. Now to detail, right? Like, you've seen the demo, you believe that it works. Now let's break down how that works. Like, how did a text model control a browser? How did a text model reason like that? So it's very simple. It's an extension of RAG, and it's called React, agents that reason and act, right? So what does that mean? An agent is given a task. We gave it 2 tasks right now, right? And a set of tools. In this case, the tools are like the browser tools, right? Like, you have the navigate to URL, you have the get elements, you have a filter elements, all those pieces. And then the task is solved by the LLM by infinitely using the tools until the task is solved. So, like, let me try this, let me try that, and until the LLM decides task is solved, it keeps doing that. So the LLM is in total control of the control flow, and it stops when the task is complete. Let's zoom in. Let's take that first question and see how the LLM worked. The user gave a query. Give me a summary of Amith KK, the software engineer. That's the query. Now, we are not talking to the LLM anymore. We're talking to the orchestrator. Orchestrator takes the query and adds this. You have the following tools. Navigate to URL, extract text, query element. It also gives a description of the tool. Like, when should you call this? Or how do you call this? What are the arguments, etc. Now, it also gives it the React prompt, which is to say that think about the next step. Don't answer, think. First, use that scratchpad to think. This is an extension of chain of thought reasoning. Repeat this thinking until you find an answer, and each time you do a thinking step, output in this format: thought, action, observation. Always give me a thought, then give me an action, which is some tool to execute, and I will give you back the observation, which is the output of the tool. Keep doing this until you get the final answer, right? So, stepping through the example, the large language model now got this prompt, and it's ready to answer it. The first thought is, to find out about Amith KK, I can start with a Google search. So I will use the navigate tool to navigate to Google directly with a query. So the next thing is that it says action, navigate to URL. At this point, as soon as it sees action, then colon observation, right? The LLM orchestrator says stop. There's actually the capability. So when you use an LLM API, right, what's being returned is not one response with the full answer. You get a stream of tokens. You get what token by token. You know how ChatGPT works, right? So when you come back, it gives the answer token by token. That's not some animation. It's just actually how the large language model outputs. It's token by token, right? So as soon as we get the finished token for this action, the execution is paused. Now the orchestrator has a job to do: navigate to URL. Now the orchestrator has some Python code that actually changes the browser page, and it changes it, and the orchestrator will tell, I have successfully navigated, like the page has loaded, you're ready to go, right? And now the LLM takes back control, and it said, okay, now it's making an observation based on what it's given. Okay, I've successfully navigated the Google page. Now what I can do is extract all the links to figure out where all I can go. Again, tool, right? Query elements ahref. So here it's tool had a description saying that the first parameter should be a CSS selector. So it's generated a CSS selector here. So now again we pause, the orchestrator takes over, gives it the answer. Here are the elements you asked for, big list of elements. Now this goes on and on and on until finally at one point the LLM is going to have a final thought. It's going to say, I have successfully visited 5 sources. I have all the information needed to write a summary. Let me call the magic tool called final answer. The moment it calls final answer, it is a declaration that I am going to stop executing, right? So now it's actually going to give the answer, and you see what the output. This is what you send back to the user. In the demo, I actually showed you the internal thinking process as well, but this is the only part you need to show the user. This approach allows the LLM to use the tools with reasoning, like how we do it, right? So whenever we started to solve a problem, we go down a route, we Google, we look at the answer. Sometimes we hit dead ends, we go back, we backtrack, right? We're like, okay, this approach doesn't work, I'm wasting too much time on it, let's try a different approach, right? So it's essentially doing that exact flow. And like, it's crazy to think that this is possible, given that we started with an autocomplete model. Remember, whenever you see an LLM use case, remember that all of this is being done with very, very fancy autocomplete, right? And that's the magical piece. Now, how did I achieve this? What is the tooling, and what open source tools are used to build this? And let me just put an interjection here. I'm actually going to open source the research that you just saw, so that you can play with it in a week or two after this talk, so that you can actually go in and use this tool, because essentially most of it was built with open source tools that I'll just show you right now. So open source LLMs, I think both the speaker before me touched on this as well, right? So open source LLMs, many of them exist. There is an abundance on them, and every single day a new one is released, right? Because there's a lot of innovation going on in this area. But as of today, and as of today, I mean as of this moment in this minute, there is no model that beats general purpose usage more than ChatGPT 4, right? That is the state of the art. No open source model has come close to consistently beating GPT 4 as of now. Now the reality is that maybe if I ever give this talk in another place, right, that will change. I'll have to update the slides because someone will make something better, and that's the point, right? Examples include Llama 2 from Meta. There is Vicuna. There is Mistral. There are a bunch of models. There are quantized versions of these models. Now the thing is, large parameter models, you need to pay a big dime. If you want to host it yourself, you need to have a big GPU, and the big GPU costs big money, right? And and that's where quantized model comes. It's like taking a 40 billion parameter model and making it a 7 billion parameter model. The results will be worse, but at least you can run it now, right? So, and a lot of people have found success, like, doing a code copilot with Code Llama running locally on a system, right? So those use cases are possible with the open source models because you have access to the weights. Hugging Face is an excellent resource. You have a model hub. You have a place to share your work. You have a place to look at what other people are doing. So it's an excellent resource to work with. And with fine tuning, as I mentioned earlier, open source models with small parameter sizes, if you fine tune them for a specific use case, you can get excellent results and probably cost savings over using GPT if you have enough scale, right? So that's where the models comes in. And let me make it clear that the demo you saw right now was running off GPT for 32K. Which is the largest context size GPT-4 available. I tried doing the same demo with Llama 2. I was not successful. It frequently, got caught in a loop of observation, and that's exactly. So one of the things I'm going to try is I'm going to try to fine tune it for web browsing and see if that helps. And I'm able to do that because it's open source. The next piece is orchestrators, right? I put that quintessential block in between a few slides back, and that did all the magic. So where do you get these orchestrators? So the orchestrator takes care of vector stores, like where to load data from. They take care of prompts. They take care of text builders, models, tools, everything, right? So LangChain and Llama Index are the leading projects there. I will give you a note of caution for the developers here. If you plan to use LangChain, and if you're estimating your stories, please estimate 10 or 20 points extra, because LangChain is currently at a point where they are rapidly iterating, which is to say that not all parts of the library work with the other parts of the library. Right, so it's very important to note that this is beta software, and this is not a reflection of LangChain as a tool. It's just that it's grown at such large. So let me quickly wrap it up. So there's a Swiss Army knife of working with LLMs, and the agent demo was built with LangChain. So rapid prototyping UIs. The UI you saw built with Streamlit. I'm just going to skip over this in the interest of time, but Streamlit allows you to build chat UIs in 5 to 10 lines of code. Finally, there are a lot of tools like this. Go ahead and look at them. This is an image from A16Z, which is Andrews and Horowitz. And finally, concluding notes. Building agents into your workflows makes your work faster, makes you do more efficient work. Open source ecosystem, thriving, available, tools are there. You can use them and please contribute to them as well. So you can push the state of the art. Finally, you don't need to be an AI ML expert to leverage this. Start leveraging LLMs today and start making your products awesome. Thank you. We don't have time for questions right now. However, this is a QR code to my LinkedIn and you can scan it and ask me questions later. Thank you.